Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I will be talking about explaining endothermic and exothermic processes from a molecular atomic point of view. And so in the last video I was talking about explaining, we were going over problems of how to identify an endothermic or exothermic process or reaction. But what's going on at the molecular level? So one way you might think about it is that the energy that's being released or absorbed has something to do with the internal or thermal energy of the system, the total thermal energy of the system. And if you remember, the thermal energy of a system is tied to the kinetic energy, the internal kinetic energy of the system, the motion of the atoms and molecules in the substance that we are referring to. And that can't be the case because, as we know, if you have an exothermic reaction, you would be losing energy from the system. Well, as we know, if you're losing energy from the system, if that energy is coming from the internal thermal energy, then that is going to be coming from the motion of the molecules. So if the molecules are losing energy, that means they're going to slow down and they're actually going to cool, right? But that can't be the case because we know in exothermic reactions or exothermic processes, they're giving off heat and they raise the temperature. The temperature gets raised. So it can't be the case that the energy is coming from the internal thermal energy or the motion of the particles. So where must it be coming from? In this case, it's got to be coming from the potential energy. So remember that the total energy of the system is potential plus kinetic. And before, in earlier videos, I talked about the kinetic energy being related to the motion of molecules, but also the energy is also being tied to the positioning of the molecules themselves or the composition of the substances that we are dealing with. And so in that case, we're talking about chemical potential energy or just chemical energy. And where is this chemical energy? The chemical energy is stored in the organization or the positioning of the molecules and atoms and the electrons relative to each other, right? So what's going on in the bonding? And so I have a couple of pictures here representing different bonds. We have our covalent bonds and we have our ionic bonds here. So when we're talking about the potential energy of a system, we're talking about how they are arranged to lower the potential energy. So in nature, everything wants to be lower energy as possible. So they're going to position themselves and arrange themselves in such a way that it's going to have the lowest potential energy possible. And that's what happens in bonds, covalent bonds, and ionic bonds. So you'll see here that in your covalent bond, you're getting shared pair of electrons. I have two chlorine atoms. They're sharing their electrons and they form a bond. And for the most part, because you have a positive, right? So you have a positive nucleus, both positive nuclei do not want to be attracted to each other, so they're going to repel each other. But at the same time, they are sharing these electrons. So the electrons are going to stay for the most part in the middle. Why are they going to stay in this area for the most part? Is because the negative electrons are attracted to the positive nuclei, and the nuclei are going to be attracted to the electrons. So staying in here is going to be the lowest potential energy, and so that is what's keeping these atoms together. So that's creating the bond. So that is where the potential energy lies. The potential energy here is between the electrostatic attractive forces between the ions themselves, very much like the positive and negative attractive forces are being attracted here as well. But here we have full charges due to a transfer of an electron from one atom to the next. So this is going to create a very strong electrostatic force. And if you remember the Coulomb's law, that is this is going to be a very strong in terms of potential energy. So they're going to want to arrange themselves and attract each other to lower that potential energy, and that's going to lower the energy in the system. So that's where the potential energy is. So when you have a chemical reaction, bonds are going to be broken, right? So covalent and ionic bonds are going to be broken, and atoms are rearranged. And it's the rearrangement of the system, the rearrangement of those particles, that's going to change the potential energy of the system. So when you're going from reactants to products, you're breaking bonds, you're reforming bonds, and then you're rearranging the potential energy of the system. And so that rearrangement of particles is going to lead to having a different amount of potential energy. And so that's where you're going to either have energy released because you've lowered the potential energy more in the product. So that energy, you're going to lower that potential energy, and that energy has to go somewhere, so it's released in the form of heat. Or you raise the potential energy during the reaction. So now the products have more potential energy than they had because of the rearrangement. And so you're going to absorb energy to get that to happen. And so, so here you can think of this in terms of bonds being broken and bonds being formed. So it's if you have weaker bonds, right? So you're going to have weaker bonds refers to a lower potential energy. So lower potential energy allows for the bonds to be broken more easily, right? So if you have weaker bonds, you can break those more easily. And then if you form stronger bonds in the products that are formed, well, that's going to be even lower energy. So you're going to go from high potential energy to low potential energy, and therefore the change in energy is going to be in the negative direction. So this is going to end up being negative potential energy, or a negative change in enthalpy. So this is going to end up being negative because the change in potential energy is going from high potential to low potential energy. And so this is released in the form of heat. In this case here, you could have the opposite direction. So your reactants could have pretty strong bonds, which means pretty low potential energy. And so you could break those bonds. It'll take more energy to break those bonds because they're stronger. And then you're going to form weaker bonds. So when you form the bonds, energy is released. So you're going from when you're separating atoms, that's a high potential energy situation. But then when you bring the atoms together, you're lowering potential energy. And how that rearrangement occurs is going to determine the amount of energy released or absorbed. And so in this case, when you break the bonds, you're putting energy in to separate the atoms. So it's going to take a lot of energy to do that for stronger bonds. And then when you put the atoms back together, or the molecules back together, then you're going to form bonds again, and that's going to release energy. But if they're weaker bonds, you're not going to release as much energy as the energy it took to break the bonds. So the overall change in potential energy is going to be higher, right? So you're going to go from low potential energy reactants to higher potential energy products. And in that case, energy overall is going to be absorbed. So your delta H is going to be positive here. So you can think of it that way. So it's really coming back from the bonds that are being broken and the bonds are being formed in the reactants and products. So that kind of explains where this energy is coming from in a chemical reaction. I hope this was helpful and clear, and if you like this video, share it with your friends. Make sure you hit the notification bell so you can be notified for any new videos I put out. Hit the subscription button, and put a comment in the comment section. Let me know what you think, and if you have any questions or anything you want me to cover in videos in the future. Thanks for joining me, and I'll see you next time.